forget that I really shouldn't do anything offline. Okay, so we're going to do a little tutorial on how to take an open loop transfer function or a plant transfer function and turn that into a closed loop transfer function for simulation in MATLAB using LSIM. So that's the goal of this, and this is completely made up as we go, so be forgiving. So I like to start off my MATLAB scripts with a clear because it gets rid of all of the variables, and then I like to close all because I always generate windows and then too many get opened. And then I like to use cells too, two percent signs in a row. So let's say parameters and system definition in this cell. So I'm going to make up a transfer function to be the plant transfer function. I'll call it G. I'll use ZPK to generate it because, which is very similar to TF, which is very similar to SS. But I'll use ZPK because then I'll have an idea of what where my open loop poles will be and zeros will be. So ZPK allows me to just specify what the zeros and the poles are. It's just like TF. We'll just do TF, and I'll have to go through a couple of times and look at it because I'm gonna just make up numbers here. So my numerator, I'll put a 0 in the numerator just for fun. So I'll do like 1 as my 2, so it'd be S plus 1 in the numerator. In the denominator, I'll put let's say we'll make it like third order. 1, let's say like 4, and then like 20. Is there like a pole 0? PZ map. Yeah. Do you guys see the other pole? I see a pole here, 0 here. I don't know. Oh wait, I only did second order, so that's all. That's fine though. It's a stable system with a 0 that's kind of low. I'm gonna increase the look. I'm gonna move that 0 out a ways because it'll be problematic if it's that close to the imaginary axis. I don't expect you to know that. Just trust me on that. So now I moved my 0 out to -10, and my poles are at -2. So it's an open loop second order system with a 0. So all right, G. So that's my plan. So just to have like something to look at while we go through this. We're going to do this. We'll have a reference. We will have a controller transfer function. And I'll make it big enough to do something larger. And then we're going to do a plant transfer function. So controller, plant, and then we'll just do unity feedback here. Or should we do a gain in the feedback loop? We get position back, so it's pretty close. So let's good. Now the controller, like a PID controller, is going to have an entire transfer function of its own, right? And I can't remember now. In Lab 7, it was a PID controller, and the gains we could change in the table, right? So
in Lab 6, we use this tungsten filter, Butterworth filter.
Yeah. Well, yeah. So the tungsten makes it discrete from continuous. So tungsten's method. But let's start off with a continuous transfer function. Continuous transfer function for a PID controller can be written Kp plus the integral term, which is Ki divided by S plus Kds. And then the plant, we just made a plant. So S minus 10, or S plus 10, I should say. S plus 10 divided by S squared plus 4S plus 20. So I'm not going to go through the whole. Let's figure out how to do it. Well, I'll just do the PID tune thing. So why the hell not? Let's do it all. Do it all at once. No problem. I haven't used PID tune in half a decade. Shouldn't cause any issues, right? All right. So what could go wrong?
Yes. You have nothing to do, so we learn something.
Let's start before this. Let's start with something I know I can do without having to go through something that I don't quite remember. Let's ignore this part and let's just use a proportional controller first. Proportional. And then I'll use this example and maybe I'll read up on PID tune a little bit and then I'll come back and do it for you guys with the same example. But we'll do a proportional controller first because this will at least give us the full, closed loop simulation thing. So if we're just going to do a proportional controller, then our closed loop transfer function, which is what we want to find, there's a formula for it, or you can derive it based on algebraic relationships defined in this block diagram. It's not too bad to find. If we called this transfer function C of S and this transfer function G of S, then our closed loop transfer function, which is Y, the output, divided by R, so Y of S divided by R of S. This is the closed loop transfer function, and from these relationships we can see that it's equal to C of S times G of S divided by 1 plus, and it's going to be, C of S times G of S again. So if you work it out, and essentially this comes from 3 equations. It comes from the equation that this what we'll call error is equal to R minus Y from the summation block. That this, which is what we'll call U, the control effort, U of S is equal to C of S times E of S from this block. And then from this block, Y of S is equal to G of S times U of S. So if you take these 3 formulas 1, 2, 3, and you solve for what the output y is over the command r, you would get this expression. And I would encourage you to review your system dynamics and controls notes for that, and I can point you to where you need to be if you would like. So this is the closed loop transfer function. In the case of a proportional controller, the C is just going to be K, right? And we are interested to find a gain for which this closed loop transfer function has desirable properties. So for just a proportional controller, which we literally went over today in the system dynamics and controls class, we just want to find a gain K that makes these closed loop poles, which come from the denominator here, right? Makes them be in a place that's desirable for us in terms of the response of the system. So step response is this response that we're thinking about when we think of the transient response characteristics. So the percent overshoot requirements or the settling time requirements, things like that. So we'll do a little proportional controller design, using a root locus technique, it's called, the root locus technique. So proportional. Controller design. So we'll do this. We'll just walk through and do a root locus proportional controller design. I'll try to motivate that a little bit if you're not familiar with root locus controller design. So the idea of the root locus is it plots where the closed loop poles are for all different values of gain K. Assuming you just have a proportional controller, it just plots where those closed loop pole locations are going to be. And you may recall that closed loop pole locations dominate how a system responds in transient response, but also steady state as well, like is there steady state error, and stability. So closed loop pole locations are things that we want to change. We want to have control over. The gain control only allows us to move the closed loop poles along the root locus. So we're kind of stuck with that. We can do a quick sketch of the root locus based on the sketching construction rules. Damn it, I only have 9% battery. I'm going to have to go get my charger. I didn't think about that. But the open loop poles were at, now I closed it, right? No, I didn't. We're at -2, -4. So like they were like here and here. And then the open loop 0 was out here, right? So the root locus, so it turns out that the closed loop pole locations start at the open loop pole locations, and they approach open loop pole 0 or open loop zeros. In this case, there's only one open loop 0, so there's a so-called 0 at infinity. There's going to be locus. Whoa. There's going to be locus out here. Following the construction rules, these guys are going to come out like this. Oh man, I'm getting a lot of lag here, so I think I'm going to have to get my charger sooner rather than later. So as we increase the gain, the closed loop poles move like this, and they come way out there. So before that sleeps, I'll be back. Grab my charger.
Your butt's
That's
falling
the
asleep.
worst.
You put too much pressure on it.
So Trey's gonna stay for the summer, right?
I'm not staying here because I didn't get a job.
Oh, okay.
That job, they said, I asked them back for feedback, but they haven't, not happy to reply again. I will stay until I get my job. I do have from my country, I had to reapply.
Okay. Whew.
Sounds like it was at like 88%.
What was that?
It was like, the battery was like 88%.
Yeah. It's this laptop's like 3.5 years old now. Battery is getting sketch. But also I have a ton of stuff running all the time. It doesn't help anything. So as we increase the gain in our controller, we can move those closed loop poles from here essentially leftward, which is actually really good news because typically we want our systems to respond faster. Turns out the further leftward our closed loop poles are, the lower the settling time and the faster the system's going to respond.
You mean fast respond, I mean it achieve to the reference that we want. Faster,
Exactly.
not rising.
Right. It takes a lot long. It's a lot shorter amount of time to get to the command position. Yeah. So leftward is good for us. We increase the gain, and in fact, it never goes unstable either. So I just happened to pick a system that works out pretty well in that regard. Wasn't totally naive decision on my part, but yeah. Anyway. So that's closed loop pole locations. They moved leftward. We're interested to find a gain that has a response that we want. The easiest thing to respond or to choose is for a certain settling time or for a certain percent overshoot. Let's do a settling time. Let's design for a settling time of like
5 seconds, 5 milliseconds.
yeah. Let's choose 1 second just to start, and we'll see how that works. Settling time of 1 second.
So in our system we simulate, we have to take this setting time also.
Yeah, so this settling time is what we're going to try to design our system to have. We'll see. We're going to pick a gain that's going to hopefully get us there. We have to choose the gain so that that's the case. Now, settling time, boy, it's just like equations, man. I don't even know if I can remember this. I think it's times negative zeta over zeta omega n. And if I remember correctly, the strange fact is that this distance
The first order.
is zeta omega n. So I want to choose my zeta omega n to be equal to 4 over settling time, which in this case we said was 1. So I want to choose zeta omega n equal to 4. So I want to choose my real part to be negative 4. So that's the gain I would like. If we go over to MATLAB and we use the beautiful root locus command. So let's do a figure and let's do our locus and we'll give it G. You give it the open loop system without the gain in it. and then you give it the gains you need. But I don't know the gains that I want yet, so I'm just going to give it G. It'll give me its best guess. So I guess I saved it. So just do, replace dumb. Don't know what it was. Okay. Oh, look at that. Approximately what I sketched. It's almost as if I knew in advance. So, I didn't though. I'm just making this up. I want you to think I'm cool. This is the main thing. That's the important takeaway. So we want to choose our gain. So this data cursor in MATLAB is really nice. We want to choose our gain so that our the real part of our pole, which is given as one of the aspects of the data cursor, because our locus is built for us to do this with. So if we choose, so it's between a gain of 3.72 and a gain of 4.13 that we cross over the -4. But this is pretty close. -4.06 as the real part there. It's pretty good. So let's just say a gain of 4.13. That's probably going to be pretty good. This is based on the second order. So this formula that I wrote down, this is the second order approximation assumption. And that is analytically just found assuming that we are not going to have any zeros in the second order. So that assumption, we are going to have a 0, so it isn't like completely true. It's going to be approximate. So let's just choose a gain of 4.13 and go from there. So we'll say our design gain, KP, is 4.13. Okay. Now, we want to know how to close the loop and simulate, right? So close the loop. We could go back to our analytic description here and plug in this transfer function, and then for C, plug in just KP for C. Or we could use this nice MATLAB function called feedback. So help feedback, and it is just wanting to know what the forward transfer function is and then the feedback transfer function. So our feedback transfer function is just 1, it's just unity, and so we just need to give it our forward transfer function, which is our plant times the gain, KP, and then it'll make a feedback transfer function for us. So all I need to do is say, so I want to call it G_CL for closed loop is equal to feedback of the forward path one then is going to be KP times G, and then the feedback is unity, and that's going to return the closed loop transfer function. So if I evaluate that, I didn't evaluate this. If I evaluate this, then it will print out my closed loop transfer function, which is pretty sweet. And then all that's left is to simulate. So if we simulate, I would recommend, so simulate, we're going to simulate the step response, right? We're thinking transient response performance characteristics and steady state performance characteristics. So a lot of times the step response is the best way to go about finding that. We know that we're stable, so we don't have to worry about that because the closed loop poles are in the left half plane, so they're stable. So let's do, to do the simulation, we'll say y equals, so this is for a unit step command. We'll do y equals step of G_CL, so the closed loop step response. And then, so that's like literally all we have to do. We can use LSIM if we want to. LSIM would allow us to simulate some other input. So, do you guys want me to use LSIM?
Do
Yeah.
both ways.
Both.
Yes.
Okay.
LSIM, when we create the signal, like the square signal for the LSIM, it doesn't allow us to change the amplitude of the signal. I have to check it manually.
Okay. Well, here.
How?
So let's do. So I'll do step first, and then I'll do another one. I'll do a different input.
Yeah.
Okay. So step input to find a step response, and then let's plot the step. So we'll do a figure. We will do plot. Oh, I didn't give it a time response, right? So when I ask it, I forget which order, so I'm going to do help step. And I'm going to look to see how I need to do my syntax. So y then t. So it'll give me a t vector, a time array, which I usually don't like to use because I don't have as much control over that, but we'll just use it. So it'll return that to me, so I would plot t step and then y step. And then I could do like x label time in seconds, y label step response y of t, and could maybe do like grid on. So let's take a look at that. So, noticing a few things here. So first of all, we've got a final value that's not 1. So if you put a reference input of 1, you would want it to go to 1, right? This is settling out at like 0.68. That's not really desirable. And the way that we would fix that, if we were going to be using PID control, is to add an integrator to it. So an integrator would help the steady state, state's error that we have here. So this is like 32% steady state error. Not great. Not really what we want. But let's see, because we were mostly focused on settling time here. Our settling time is the time at which it gets within, is it 5% or 2% of the final value and never leaves it again? 2%? Yeah, so it's like somewhere in here, I would believe. It's hard to eyeball that, right? So how are we going to know how well we did? Well, I like using good old-fashioned step info, okay? So I will do evaluate step settling time via step info. So if I don't remember step info's syntax either, so the order it uses. So step info YT, that should do it. So even if I just do this, if I just do step info of Y step comma T step, and I run this, it will print out in the window my settling time, 0.97 seconds. Nailed it. Right?
We put 1, right?
We were designing for 1 second. 0.97.
Even better.
Even better. That's right. Of course, there's a trade-off, right? The trade-off is that we probably had to flow more whatever our control effort is, current or whatever. So it's not like it's free. It costs, but when you're within 3% with your design, oftentimes you're like, that's pretty good. You could tweak it and get it more precise if you wanted. Okay, so we did it. We did a proportional controller that met that design spec. However, it needs some integral in there, right? It's just a proportional controller that gives us the settling time we want, but it's like still like doesn't go to our final value, even close really. So we need to improve that, which we would do by adding an integrator. And I think that I'm going to hold off on. Nah, we'll do an integrator. I want to embarrass myself in front of Shelby because I always got to call you out. I haven't reviewed my notes on PI control for a while, but I'm pretty sure I remember how to do this. So you guys want to do an integrator compensator on this? Yeah, okay. So let's do it. We were going to do LSIM. Would you guys prefer I do an integrator now or do LSIM first? I'll do them both if you want. Okay, well let's do the integrator first, and then we'll do an LSIM, just for fun. Okay, so let's do integral compensation. So the idea with this is we take our proportional controller and we just multiply it by another transfer function. So we know we want to add an integrator in because integrators, if you've gone through that argument before, if you add an integrator into your controller, it's going to reduce steady state error. If it's a finite steady state error and you add an integrator in, you're going to get 0 steady state error. Okay, so that's good. That's good for a step input. So we know, okay, we want 0 steady state error. That would be ideal. Let's put an integrator in there and see if we can make it happen. So if you put an integrator in, so you can just take, so right now our controller is just a gain K, right? KP. If you just put an integrator, if you just multiply this by 1 over S, unfortunately, really bad things happen to your root locus. Okay, so what happens is you end up with you put a pole here, you end up with locus here, and these two go off to like infinity, like this. So that's like way different performing. So like if you just toss an integrator in, it's really not helping you out. Like it's really messed everything up for you. So instead of doing that, what we'll do is we'll put the integrator in, and then we'll also put in a 0 in pretty close. So we'll put that S in the denominator, but then in the numerator, instead of just having 1 in the numerator, we're just gonna put in S plus, we'll start off with like, it's really hard to choose this. I'll start off with like S plus 0.5, so it's going to affect, it's going to put a pole, a closed loop pole in here, but if you look at the locus, it's in here. There's locus in between this pole and the 0. And notice that this means that it's going to be a very close to your real axis pole. Kind of going to mess up your transient response potentially. So like it could slow things down, could cause problems. So we might need to move this 0 leftward some, and we could play with that where that 0 location is. Yeah, well, it's your second order approximation. You're pretty much like throwing it out the window at this point. But you're saying, okay, I designed the proportional controller to be pretty good transient response wise. As long as I have this 0 in there and their effects kind of cancel, pole 0 effects kind of cancel, but not exactly. I like, hopefully I won't mess up my transient too bad. So that's the idea. So we'll put it in as a compensator. So I'll say G, well, I'll actually call it C, I. So this is the compensator transfer function for the integral controller. And we're going to do TF of, and so we could use ZPK also, but let's use TF. This is pretty easy in this case. So 1 plus, not plus, comma, say 0.5. And then in the denominator, we have 1 comma 0, right? So s to the 1 and then plus 0. And that's our compensator for the integral controller. Now, our compensated system, so our G closed loop, really we should have called this like G closed loop, I'll call it G closed loop P. I'll do underscore P. And then we'll call this one closed loop PI equals. What we need to do is we need to use our feedback again. And this time, so what we'll do is we'll use our you can either use your original KP, which I think is so a couple ways you can go here. I like to look back at the root locus. So I'm gonna pause that one. And we're gonna come back. We're gonna look at the root locus with this. So I want to do an R locus of, now my open loop system is my KP times my CI times my open loop G, right? And then the feedback is still unity. So let's take a look. Oops, it's big P. Let's take a look. Let's make it a figure. Okay. So why am I not seeing? So there's my integral compensator. And there's my open loop. What am I doing wrong? And sometimes I don't put this gain in, but I don't think that's going to matter. Where's my locus? Oh, that's because it's only doing it for one gain. I was doing feedback syntax. Okay, we're back in business. Confusion is gone. Here we go. So now we've got the same root locus as before, pretty much, but we've got this pole and 0 near the origin that's happening now. This is our integral compensator. Now, we can go back and choose a new gain that will be multiplying the old gain by. So this one, the new gain, is like, it's somewhere in there still. It's around, so this gain is going to be a multiplier of the previous gain. So it's almost around the same gain. So I think we should just stick with the same gain, and we might need to tweak it later. So let's see, but remember, our compensator here might screw up our transient response. That might happen. So let's take a look. Let's do feedback. So, step simulation. So, the closed loop transfer function is going to be KP, well, open loop is this, and then feedback is that. And then we just want to do the same thing, so we'll do Y step. In this case, it's going to be PI equals step GCL PI. And we'll use the, this is why I like to keep all the times the same. I'm going to edit this, and I hope that you guys don't hate me for it. I'm just going to do Y step. I'm going to just do one time array, TA, and I'm going to make it linspace from 0 to 2 seconds, and I'll do like 150 points. And then I can do step, and then I can hand it my TA array. So it uses my TA array, because I don't really want to just get different time arrays out. So I want to be able to compare them if I want. I want lots of things. I'm also going to make this step P instead of step PI, instead of step regular. Okay, so we're getting there. Good, and I'll send this out to you guys. It's fine. So good step response. Now let's go ahead and plot it. So TA Y step PI. Error. 24. Oh, I thought I fixed that. Okay, so what we see is that, and this is pretty common when we do the compensator like this, we get a pretty similar transient, and then we get this slow ooze to our steady state value. It's not, it's pretty slow though, right? We aren't in love with that, but that is how these compensators tend to be when you first design them. So let's say I want to move my 0 a little bit to the left, and see if that helps me out. Like I'll put it at like twice as far out there, and let's see if that helps speed it up. Yeah, that's faster. And then let's go, like, it's not really, I'm not sacrificing a lot in my initial response either, so I think that I can be more aggressive with it. I'll put it out another factor of 2 out. And now it's getting pretty good, right? It's, you know, we could maybe go a little bit further without getting into too much trouble. So like 5? Oh yeah, let's do it. Let's go big.
Oof.
So pretty good. I think we lost some settling time there, but we gained some steady state error. So this is one of those things. It's a bit of a trade-off between your different performance requirements.
this case, when the suit up would be 1.2.
Yeah, and so my percent overshoot here is like 21% or something. So I could compare the two also. So it'd probably be best to, I'll just do this plot down here instead of doing multiple. So I'll plot the proportional controller and then the proportional integral controller that we designed. And then I'll add in a legend. The first one is P control. Second one is PI control. So
This is without I. And
So yeah, so P is the transient's a little bit better for our P control. PI control, the steady state's way better, but we lost a little bit in our transient. So we could do some things. We could start to increase the gain to see if that helps get us back under with our transient, with our settling times. Our settling time is probably more like 1.5 now instead of 1 second. So we sort of lost that spec a little bit. If we looked at it, so what I'll do, since we really are only looking at the one property, I'll call this SIP, and then I'll just print SIP dot settling time, and then I'll do the same thing for PI. So my settling time was 0.95 apparently. I don't know why. Why did that change? I thought it was 0.97. I don't remember. But anyways, it's more than meets the spec. Oh, I know why. It's because we changed our time vector, and so it got, I think there are more points now. So it was like we were at 0.95 seconds, now we're at 1.58. So we probably should iterate a little bit and get a little bit better gain. So for my gain, for my integral control compensator, I'm going to add a gain term to it. I'm going to call it KI, but it's not the same KI that we have seen before. Or should I call it something else? KII. I'll do K. Well, actually, I won't call it anything. I'll just put the number in. How about that? So I'll just put the number in as, let's call it like, let's do 2. Let's do a gain of 2. Just to see. Maybe this is going to help. I have a suspicion that our settling time is going to get better for the PI controller if we increase the gain. So let's try it.
Yeah.
Yeah, I did. Got a lot better. So it actually,
Same as the PV.
yeah, it's actually even a little bit better, right? So I should probably print out what these are. So what do you do? Is it sprintf in MATLAB? Or just sprintf? Sprintf, and then I think it's like, so I'll say, what is this? Proportional settling time. And then percent G, oh goodness, it's like, I don't know if I know how that formatting correct. Will just print F work?
I think you have to do F for now for S.
F print.
So you have to do the new line.
Ah, yeah. Boom. Okay, but we were a little too aggressive with that game. You know, 1.5. We could try that. You could of course automate this. Ooh, 1.03. It's pretty good. So like, okay, so we designed controllers. We've now simulated them. There was a request for an LSIM simulation. We'll finish with that today. An LSIM simulation. I think I'm gonna have the systems group watch class watch this lecture.
Really helpful.
So okay, so then let's do a. It's worked out surprisingly well, given the fact that I have just made it all up as we've gone. So hardly any hiccup. So let's do a. What kind of input do you guys want? It could be just like some function that we use, or it could be some arbitrary thing. Yeah. I don't know the syntax of that one. So what I'll do is, let's do a sinusoidal ramp. Just for the hell of it. Reference. So if we want, we have to construct for LSIM. LSIM is expecting us to put in inputs and initial conditions. It is going to, so zero initial conditions is typically what we do unless we have a specific case we want to find the transient for with initial conditions. So we're going to think about what a sinusoidal ramp function would look like, how to construct it. I think it's easy enough to just write a simple anonymous function for it. So I'll just call this like FSR for sine ramp. And it's going to be a function of t. So for a given time, I'm going to want the output to be, let's make it just a unit sinusoid and a unit ramp. So sine of, let's do 1 hertz, so 2 times pi for the period, plus, I don't even need a phase on there, and then plus t. Then I'm going to give, I'll just use my time array. If I plug my time array in here, it should just work. I don't need to do any of the dot times because these are all, whenever you have an element-wise operation, you need to use dot operator in MATLAB. But in this case, we don't need it because none of our operations are ambiguous. They're constant times arrays, which it knows to do element-wise. Sine of an array is just an array of signs. And then if you add 2 arrays of the same size, it'll happily do element-wise addition. So no need for any element-wise operations there. So, and we can just use TA. So we can just go ahead and just do this. We're going to need to do a help LSIM to figure out the order of our inputs here, of our arguments. System U as input T, you don't even have to give it an initial condition. It'll assume it's 0 unless it's otherwise specified. So yeah, sys UT. So we're going to do YSR equals LSIM. We're going to want to use we'll use our PI controlled closed loop system. So GCL PI, our input is going to be FSR of TA, this input function, and then our time array is going to be TA. That's going to give us outputs. So just like step, it will do a graph for you, but I prefer to just get the output and then do it. It's a single input, single output system, so YSR is just going to be a single array. If there were multiple outputs, we would have to have a matrix output, but this is just going to be an array. And then we can do a plot. So figure plot TAYSR. We could plot the command and the response. How's that sound? So we'll plot first the command. So FSR TA, and then hold on, and then plot YSR. So this is the actual response of the system. And let's do X label time in seconds, Y label. So this is going to be the sinusoidal ramp response. And we could do grid on. And we'll do a little legend which says command and response. Yeah, I think we're ready. What do you guys think? Is it a go? Boom. Satisfying. Satisfying. Let's do, let's increase the frequency a little bit so we get more oscillations in there. So we'll do like 4 times that frequency. So the command is doing this. The response can't keep up with that. If it was slower, it'd be better, but it can't keep up with that. So if this was the command that we were expecting to put in, this is what we really wanted to do, we would need to change our controller. This is a really, really difficult command to keep up with, though. I mean, a relatively high frequency, increasing ramp sinusoid. That's tough. So I'm not surprised that it's hard to keep up with it. But like before, so if we just slowed it back down to being 1 hertz, and we simulate it for a little longer. So if I make my TA, where did I define it? Up to like 6 seconds. We did it again. We see that at 1 hertz, we're close. Not you. We're close, right? So, yeah. I don't know. This is fun. I enjoy it. Any other questions? Did I answer anything you were curious about in there? I hope I did.
Maybe we go back to see the actual things that we have to do in the exercise.
Yeah, and the PID tune, so you guys don't actually have to do, the part that was probably the hardest to follow was the design process of choosing the gains and the root locus stuff.
Yeah.
You don't actually have to do any of that because you can use PID tune as long as you use it. And I'll show you how to use it. I'll do an extra lecture on that. Okay? Okay. Good times.
Right.
All right. It was fun. I enjoyed it. I hope you guys liked it.